Welcome to ECE CS 552, lecture on Arithmetic and Logic. In this lecture, we will cover the design of circuitry for basic arithmetic and the arithmetic logic unit. Initially, we'll review number representations, then we'll talk briefly about addition, subtraction, how to build an ALU, and then how to support logical operations like ands, ors, and shifts. And we'll conclude with a discussion of overflow and flags. Later on in the semester, we'll be covering in more detail other arithmetic operations like multiplication and division, as well as the floating point representation. These are not crucial for the project, so we defer coverage of them until later. To briefly review, you should remember from 352 and even 252 that having n bits to represent a value allows 2 to the n unique combinations. For the purposes of the arithmetic discussion that's coming up, we'll be using a subscript notation where the bits are numbered from left to right. If you think about just a sequence of 32 bits, it really has no inherent meaning. All of its meaning is derived from how it's interpreted. So for example, if we have a function f that interprets a 32-bit value, that function f can treat it as an integer value. It could treat it as control signals. It could treat it as an instruction word. It could treat it as pixel values in a graphical display. Common 32-bit types, and types again are what determine how bits are interpreted, include unsigned integers where no negative values are possible, signed integers where both positive and negative values can be represented, single precision floating point, which we'll talk about later in the semester, as well as MIPS instructions, which you'll become very familiar with. Let's talk first about unsigned integers. Unsigned integers are represented using a weighted positional notation that's summarized here. Basically what this means is that each bit position is multiplied by 2 to the power corresponding to the index of that bit position, which allows us to represent both very large and very small numbers with different combinations of zeros and ones. So these are just normal binary numbers, which I'm sure many of you remember, or most of you remember from your previous classes. Here's a couple of examples. The maximum value that we can represent with an unsigned integer representation is all ones, which is shown here. For a 32-bit value, it's a little bit over 4 billion. The minimum is 0. So the range can be, in general, expressed as anywhere from 0 to 2 to the 32 minus 1. Signed integers are a little bit more tricky. We use a representation called 2's complement, where all of the other bits are interpreted the same way as they are in unsigned, except the most significant bit, also called the signed bit, is in fact treated as a negative value. So if the most significant bit is a 1, we are going to add a negative 2 to the 31st to the resulting value. In this case, because the maximum value in the positive end now has a leading 0, our range is only half of what it is for unsigned numbers. So we only get up to about 2 billion, and our minimum is similarly about negative 2 billion. The range is a little bit asymmetric for reasons that we'll see in a bit. More formally, the range can be specified as from minus 2 to the 31 to minus 2 to the 31 minus 1. Again, the number of values here is still 2 to the 32nd because we need to reserve one representation for 0. The quick trick for converting a number or determining what the 2's complement or the negative representation of a number is if you have a negative number like minus 6, is to write it out in binary. You invert all of the bits and you add 1. Here's a quick example that you can review if you don't remember how to do this. Why do we use 2's complement? Why not use sign magnitude? Well, it turns out that 2's complement makes the hardware simpler. We can use more or less identical arithmetic hardware to perform arithmetic on both unsigned numbers as well as 2's complement numbers. That's the main motivation for using this representation, which is a little bit counterintuitive. But it's the same kind of reasoning that we use to use decimal numbers rather than Roman numerals. Even though we can express numbers using Roman numerals, arithmetic computations are cumbersome and difficult with them. The figures on the bottom here kind of illustrate this. So in the sign magnitude case, one of the weird things that happens is that we actually have 2 representations for 0, positive 0 and negative 0, because we always have the sign bit available to represent plus or minus. Minus 0 is not really all that useful of a concept. So in a sense, we're wasting our representations by doing that. In 2's complement, we don't have that. Instead, the same representation that would be minus 0 in sign magnitude is used to extend the negative range one further, in this case to minus 4. Here we have a couple of examples of addition, and next we'll talk about subtraction. So the first example shows the addition of two 4-bit unsigned numbers, in this case corresponding to decimal values 3 and 10. The sum you expect there, of course, is 13. You can work through this in detail on your own, but if you simply do column-wise bit addition, you can see that the answer turns out to be the correct answer. Similarly, we can do 4-bit 2's complement addition on these same 2-bit patterns, but if we're interpreting them as 2's complement numbers, the second number now actually represents -6. And here also we see that simply doing the bitwise addition and carrying into the third column there as shown still gives us the correct answer. We still end up with a -3. So this example illustrates how the exact same algorithm for adding two multi-bit numbers together will give you the right answer, whether you're dealing with unsigned or 2's complement representation. Rather than building separate hardware for doing subtraction, since we have a representation for negative numbers, the way we normally do subtraction is to simply convert the second operand into its 2's complement and then use the existing adder hardware. So for example, if we're subtracting 2 from 3, we can see that again the correct answer is computed with the same hardware once we've taken the second operand and converted it to its 2's complement representation. The building block that we use to construct multi-bit adders is called a full adder. A full adder is used to perform the computation that's needed or the logic for a single bit position. And a full adder is called a full adder because it actually takes 3 operands. So at each bit position, remember, we're not just adding the two values of the bits at that bit position A and B, but we also have to accommodate a possible carry in. So there really are 3 bits coming into that position, and there are 2 outputs. One is the sum for that column, but also the carry out, which then has to be carried in to the next column or next bit position. This table summarizes the truth table for a full adder. In blue, we see the values for carry out, and in yellow, we see the values for sum, where those values are non-zero. Once we've designed a full adder based on the truth table on the previous page, we can simply daisy chain them together in order to implement a wider adder. So in this case, we see an example of a 32-bit adder starting from the left and propagating carries from each position to the position on its right in order to propagate the carries and compute the final sum. We can extend this ripple carry adder to also perform subtraction by adding an inverter to the second operand B. So we can invert each of these bits coming in, and we can also feed in an explicit carry of 1 into the leftmost or least significant bit position. Remember, flipping all the bits and adding 1 is equivalent to taking the 2's complement of a number, so this allows us to in fact implement subtraction. We can combine both adding and subtracting into the same piece of logic by adding a control signal, which whenever it's set to 1 will trigger a subtraction, and that control signal is used to govern an exclusive OR gate that now replaces the inverter shown on the previous slide. An XOR gate has the property that if the right-hand input in this case is a 1, it'll invert the left-hand input. If the right-hand input is a 0, it'll simply pass through the left-hand input. That allows us to conditionally complement the second operand. Similarly, that operation input is fed into the carry in of the least significant bit position. So whenever operation is 1, we'll be doing a subtraction of A minus B. Whenever operation is 0, we'll be doing an addition of A plus B. We also want to be able to support a number of logical operations. These are implemented in a bitwise fashion, and they're very straightforward, so we won't spend much time on them, but performing a bitwise AND or XOR NOR, whatever logical operation you might need, is simply implemented with 32 gates in parallel, computing all of the 32 bits of each operand, the result for all of the 32 bits at the same time. Shifts and rotates are a little bit more complicated. We'll talk a little bit more about them. Typically, these come in a number of flavors. You might have rotate forms where you rotate bits to the left or to the right. You might have shift forms, shift logical forms, where you are shifting the bits to the left or to the right and replacing the missing bits with zeros. There's also an arithmetic form of shift right, where the most significant bit, which again, in an arithmetic context with signed numbers, 2's complement numbers, corresponds to the signed bit, actually gets replicated. So as we shift to the right, all of the missing upper bits are replaced with whatever the signed bit was. If it was a positive number, we propagate zeros into those positions. If it was a negative number, we propagate ones. And the reason for supporting that is that we can actually maintain the correct arithmetic semantics corresponding to that right shift, if we think about it in terms of a division by a power of 2, if we maintain those upper sign bits. Here we show the structure of a shifter. A shifter is typically implemented using a number of multiplexers that is logarithmic. The number of levels is logarithmic with respect to the width of the operands. In this example, we have 8-bit operands, and the log base 2 of 8 is 3, so we have 3 levels of 2-to-1 muxes in the shifter design. And the way this works is, at the first level, we are going to shift by 1. At the next level, as you can see from the wiring, we shift by 2, and in the third level we shift by 4. And each of those shifts is controlled by the corresponding bits of the shift amount. So if all 3 bits in S0, S1, and S2 are set to 0, then the values will simply pass straight through. However, if the values are set to all 1, as you can see by tracing the path for bit X7, we've shifted it all the way over from bit position 7 to bit position 0 for a shift of 7. What's shown here is only the right shift logic. All of the missing inputs are going to be 0. The left shift logic is similar. You can imagine it's symmetric. And then to support rotates, instead of providing 0 inputs for the missing inputs, we simply provide the corresponding wraparound inputs from the other side of the shifter. We put these all together to make up the arithmetic logic unit. It looks something like this. We'll have a block that provides the addition. We'll have the invert signal that allows us to either perform addition or subtraction. We will have the logic units like shown here for the AND and the OR, and then at the output side of the arithmetic logic unit we'll have a multiplexer that allows us to choose whichever operation is currently being requested by the instruction that is executing in our processor at the time. And so the 2 inputs come in on the left, the result comes out on the right, and the control signals coming in at the top will determine which operation is being performed. There's a few additional complications here that we have to deal with. The first of these is arithmetic overflow. So just like in decimal numbers, if we only have 3 digits to represent a decimal number, we really can't represent any number larger than 999. We have the same problem with binary numbers. With n bits, again, we have only 2 to the n combinations. And so the range is, as we discussed before, for unsigned from 0 to 2 to the n minus 1, and for 2's complement from minus 2 to the n minus 1 to 2 to the n minus 1 minus 1. So any result that falls outside of those ranges, either for unsigned computation or for signed arithmetic, we have to deal with somehow. So for example, if we're dealing with 3-bit numbers and we add the number 5 and the number 6, the result is going to be greater than 7. In other words, it's going to be a number, in this case 13, that cannot be represented with 13 bits. So what do? Well, typically we will add logic that will detect the overflow case and somehow communicate that to the programmer or to the user. So in the case of unsigned arithmetic, it's very easy. If we detect that a carry has occurred out of the most significant bit, into the bit that's 1 bit to the left of the most significant bit, then we detect that an overflow condition has occurred. For 2's complement, it's a little bit more complicated because we can't simply look at the carry out from the most significant bit position, because specifically when we're dealing with addition of 2 negative numbers, we actually have that carry occur, but we can simply ignore it in that scenario because the answer is actually correct. 110 in this case is minus 2. That is the correct answer. So for 2's complement arithmetic, we have to do something a little bit more sophisticated to detect overflow. If we step back and think about it a little bit, we can sort of reason our way through the process of detecting overflow for signed arithmetic. If you think about it, it's not possible for overflow to occur when the two operands have different signs. So if I'm adding a positive number to a negative number, the sum is definitely going to fall within the allowable range. And similarly, if I'm adding a negative number to a positive number, the same reasoning follows. Really, it's only when both numbers are positive that the sum can be greater than the maximum range, the maximum of the range, or if both operands are negative, that it can be less than the least number that we can represent. However, looking at signs of inputs is not sufficient either, because there are many cases where two positive numbers added together are still the sum is perfectly possible to represent without any overflow. The same is true for two negative numbers. So we have to dig a little bit deeper than this. And again, the reasoning follows from the point raised on the previous page. We know that the sum of two positive numbers should never be negative. So if in fact we perform the computation where both operands are positive, and the sum turns out to be negative, we can in fact infer that overflow has occurred. And similarly, symmetrically, if we're adding two negative numbers and we end up with a positive sum, we should also conclude that overflow has occurred. So it's actually pretty straightforward, and the logic is shown at the bottom of the slide. Detection of overflow for subtraction is very similar to this. Remember, to do subtraction, all we're doing is taking the right-hand operand, in this case b, and flipping its sign. So all we really have to do to detect overflow on subtraction is to flip the sense of the logic checking that we're doing on the sign bits. So again, the logic is shown at the bottom of the slide here. A question for an architect is, what do we do on an overflow? Depending a little bit on the context that you're executing in and what high-level language semantics you're supporting, we may not have to do anything. For example, in the C language, there really is no semantic support for overflows, so we simply ignore them. When they happen silently, and the programmer has really no automatic way to catch them. They have to explicitly program in checks for overflow conditions. Other languages, such as Java, have richer exception semantics and may or may not need mechanisms in place to detect and deal with these overflow exceptions and invoke some kind of exception handler for them. Other ways that architecturally we can deal with these is to simply set a flag or a condition code. Oftentimes, the overflow flag might be what's called a sticky flag. What this means is that it's not set in a precise way in the same way that a normal exception would occur. We would simply set the flag, and then there would be software support, another instruction in the instruction set that would allow us to check that flag. But by the time we check it, computation may have advanced past the point of the instruction that actually set it. And by the word sticky, we mean that if any instruction sets it, it doesn't get cleared by subsequent arithmetic operations. It stays set until it's explicitly cleared again by a specific instruction that is checking it and or clearing it. We can also have a precise trap or exception for this condition, for an overflow condition. Oftentimes this is a maskable trap, because sometimes we simply don't care, other times we do care. So the instruction set might have support for either trapping on the overflow or not trapping on it. For example, MIPS has one flavor of add that does trap and a different flavor of add that does not trap. The trapping form is useful mostly for extended precision in software. So for example, if you're emulating 128-bit integers for some reason, maybe you have an application where you need very large integers, you can use these traps now to detect cases where arithmetic operations on the less significant chunks of computation are generating carry-out values, and then you can trigger computations for the upper chunks of arithmetic operations. Other flags we typically want to compute as a result of arithmetic operations are 0 and negative. 0 is very straightforward. We simply OR together all of the bits of the result and then complement that result of that OR. And for the negative flag, we simply have to look at the sign bit of the result. The only complication with 0 and negative is that we may also want a correct answer even when the answer has overflowed. So for example, we may want to know that the result of a minus b in this example, for example, typically if we're trying to compare for inequality, if we want to see if a is less than b, we'll simply subtract b from a and check to see if the result is negative. Even if the value ends up overflowing, we would really like to know get the correct answer for the comparison in this case, because the overflow doesn't really matter. We're not interested in the answer, the actual difference between the two. We're only interested in the sign of the difference. So for in this case, to handle this kind of case, we can simply take the sign bit of the result and XOR it with the overflow condition that we're already computing anyway, and that will then correctly set the negative case even when there's an overflow condition. Summarizing this lecture, we covered briefly binary representations for numbers, including signed numbers using 2's complement and unsigned numbers. We talked briefly about arithmetic, how to build a full carry adder and a multi-bit ripple carry adder based on full adders, how to detect overflow, negative, zero, and also we talked about logical instructions like shifts, ands, and ors. Coming up, we'll be talking about more sophisticated mechanisms for performing addition, and later in the semester, we'll talk about multiply and divide and floating point.